welcome back. For those that are standing in the back, can you please come up? There's a few spaces here and a few dabbles amongst the crowd, just so that if we're full house, we're going to close those doors. So if we can find seats, that'd be fantastic. Welcome back to the afternoon, the second half of the Data Science Festival. Hopefully everyone had a great lunch. How many of us signed up for the competition, the popcorn competition? Yes. Who wants 500 quid? Make sure you go downstairs before the end of the day. Something else to mention is at the end of today, you're going to have the opportunity to network with different people in the space bar just below. So from 5 to 6, there's going to be networking if you'd like to join. But to introduce our next speaker, she is from NVIDIA. Her name is Ekaterina Sirazitdinova, and she'll be speaking about Multimodal Generative AI Demystified. So, as a senior data scientist at NVIDIA, she specializes in leveraging AI techniques such as multimodal generative AI and large language models to tackle computer vision and natural language understanding challenges. She is skilled in end-to-end AI production, encompassing the entire process from development to optimized deployment, whether it be in the cloud or on the edge. Previously, Ekaterina was a research engineer applying deep learning to medical image analysis. She has also authored several peer-reviewed journals and conference publications on various applications on image-based 3D reconstruction, localizing, and tracking. She received her PhD in computer science and her master's in media informatics. She also holds a diploma in business informatics. Welcome, Ekaterina.
Thank you very much for this nice introduction, and I'm super excited to be here on this lovely Saturday. Today I came here to talk about multimodal generative AI, and usually what I do is when I present at events, I try to check how many data scientists are here, but we are at a data science festival, so I think the majority of you are data scientists. And what I can tell you, I know how you feel. I know how you feel for the past 1.5 years. At least that's how I feel recently. While most of us are still trying to fine-tune hyperparameters of convolutional neural networks, the technology like generative AI, comes as a huge tornado and sweeps out everything on its way, and even makes some jobs obsolete. But before we continue talking about multimodal generative AI, I'd like to take a little look into the retrospective. So what we had in the past was a huge number of different architectures. We had specialized architectures for image processing, like convolutional neural networks. We had GANs for image generation. RNNs were largely used for speech and text processing. And reinforcement learning was mostly used in robotics. These days, things changing, right? The reason why it's happening is that these architectures basically, they were good, they are still very good, and they're still largely used, but they're very specialized. So for example, to train a convolutional neural network to recognize cats, you would need a data set which was collected and then labeled by humans, and then using these annotations, you would train a model which would be good at performing one and only task in recognizing cats. And if you want this network to be able to recognize dogs, unfortunately, there is no chance unless you train this model again, unless you collect a new data set. You can imagine that if you want to build something like artificial general intelligence, this is not very sustainable. And I believe a sustainable approach has been found, and this is multimodal generative AI. So by multimodal generative AI, we understand, working with all types of data, because the world consists not only of images or text, the world has all kinds of data, right? And being able to get all these kinds of data and to train some sort of an architecture in an unsupervised way, I think this is the key of, progressing towards something like artificial general intelligence. In the multimodal space, what we have is some sort of a foundation model, usually based on the architecture called the transformer architecture, which consists of billions of parameters. And it's usually trained on large amounts of data to the scale of the whole internet. These models are zero-shot learners. By zero-shot, we understand the capability of a model make predictions based on the data it has never been specifically trained to predict. Like when we take a foundation model for images, for example, we would expect it to know what are cats and dogs without specifically training and fine-tuning this model into recognizing cats and dogs. And there is a large evidence that this technology is already here and it's very useful. So in the figures I'm showing you here, they are taken from the paper Sparks of Artificial General Intelligence published by Microsoft. And they were able to show that the GPT-4 model, GPT stands for Generative Pre-trained Transformer, and GPT-4 is the model by OpenAI. In this paper, they were able to show that this model is able to perform zero-shot learning tasks with the accuracy of 82%. 82 is already a great number, and it indicates that these techniques are already very useful. In another example, which I really like, it demonstrates you how multimodality can further contribute into, well, quality of the predictions. So the blue bars are showing the performance of the GPT 3.5, also known as the early version of ChatGPT model. And so this is the performance of this model on some of the exams, and while it did perform well on some of the exams, it still kind of underperformed on another. And by expanding this model to multimodality, you see the green bars, it's the performance of GPT-4. And especially with dark green, it's by adding specifically imaging. They were able to achieve a much better performance. So this improvement is no longer incremental, it is substantial. Another example which I really like, in the same GPT-4 technical report, they were able to show that AI, multimodal AI, is able to reason about humor. So by showing this image where you see a smartphone which is being charged by something which resembles a VGA connector. And those of you who remember VGA connectors, you know that these were some connectors to connect your old school monitors to your workstation, for example. And you know that it's no longer used, well, to charge mobile phones at least. The GPT-4 was not only able to recognize that there are multiple panels in this image, but it was also able to precisely describe what's happening there. And it was also able to reason why this situation is kind of funny. I think it's really beautiful. In the next demo, which I'd like to show you, we're demonstrating the use of multimodal technology like text-to-speech and speech-to-text connected to the text generation capabilities of large language models. This demo has been created with the support of our partners, Convai, and it basically shows you how we will be experiencing gaming in the future. So where you as a player would enter the game, and you all know that in games we sometimes have non-playable characters, also known as NPCs. So from now on, these NPCs, they will be also able to talk back to you, they will be able to interact with you, and you'll be able to have meaningful conversations with them. So let's take a look at this demo.
We are thrilled to showcase an immersive and dynamic interaction between a player Kai and a non-playable character named Jin. This captivating ramen shop scene was created by NVIDIA using the latest RTX rendering technologies. NVIDIA collaborated with Convai, an NVIDIA Inception partner, to showcase how developers will soon be able to use NVIDIA Riva, Nemo, and Audio to Face for AI-powered speech, conversation, and animation. These models were integrated into the Convai Services platform and fed into Unreal Engine 5 and MetaHuman to bring Jin to life. Please take a look.
Hey Jin, how are you?
Unfortunately, not so good.
How come?
I am worried about the crime around here. It's gotten bad lately. My ramen shop got caught in the crossfire.
Can I help?
If you want to do something about this, I have heard rumors that the powerful crime lord Kuman Aoki is causing all sorts of chaos in the city. He may be the root of this violence.
I'll talk to him. Where can I find him?
I have heard he hangs out in the underground fight clubs on the city's east side. Try there.
Okay, I'll go.
Be careful, Kai.
I really love it, and I think it's the gaming experience of the future. So let's learn how this technology actually works, how multimodal generative AI works. And the idea here is that the core of this technology, as I mentioned, we have some sort of a large model. We also call this model a foundation model. Foundation model is the model which has been pre-trained on large amount of data, typically in an unsupervised way. And in case of multimodal generative AI, this data we pre-train this model on can be of different types. It can be text, video, sound, images, code, and structured data. And then what we expect from this model is some certain behavior and helping you to solve some tasks. And you can train this model for specific tasks, right? Now also what we observe the recent days that it's not only a single model anymore, but kind of an ensemble of models. We call it also a mixture of experts. And this technology is becoming more and more popular because we see that it is usually more performant and provides you with a better quality. So in multimodal, mixture of experts is often used. And in order to pre-train a model from scratch, I'll repeat myself, but we need 3 important components. We need a large amount of data to the scale of the whole internet. We need billions of parameters to encapsulate all these patterns and knowledge from the data in this model. And we need unsupervised learning because, as I mentioned before, it is not sustainable to label the whole world of data. Once this model is trained, it can be further adapted to the downstream tasks. And by this downstream task, we can understand a huge variety of tasks. You can be really creative here. So you can generate code with these models. You can use these models for machine translation to translate from one language to another. You can further fine-tune this model to summarize text or summarize an image or a video. You can use it for image captioning, video captioning. You can use it for sentiment analysis in text or in video, in audio as well. You can fine-tune it for question answering as a dialogue system, as a chatbot. And you can also use it for typical computer vision tasks like object recognition, object segmentation, body pose recognition, and many other video analytics tasks. To learn further how to actually work with multimodal architectures, I think we need to take a little pause and look at the basics. And as I mentioned before, in the basics, we have the transformer architecture. And the transformer architecture, as I'm showing it to you here, is actually the way how it has been published in the paper Attention is All You Need from the year 2017. You can see here that the typical transformer architecture, well, we have actually different representations of it, but this is the classical transformer architecture. It consists of an encoder, which analyzes text. So classical transformers were designed for language and text processing. And the decoder part is used to generate new text based on the inputs it analyzed in the encoder. Transformers work with numbers. So, of course, you have, well, data in all kinds of formats, but you know that deep learning models, they all need numbers. So in order to be able to process your data in the transformer, you first convert your data in the format which is called tokens. The token is basically a numbered representation of your text which you can think of as a sort of a lookup table where you map some certain words and parts of these words to some integer numbers. And this representation can be learned or can be engineered. But then to further capture the relationships between these parts of the words and to bring some semantic meaning in them, you further learn the representation, which is called embeddings. And embeddings are very powerful representation of our objects. You can represent everything in embeddings. You can convert your images to embeddings by using architectures like vision transformers. You can represent sound as embeddings, because essentially all data we have can be transformed into numbers, and these numbers can be transformed into embeddings. And this is the key to multimodality. Another great addition and great contribution of the transformer architecture was the so-called attention mechanism. Attention mechanism is something which allows you to differentially weight parts of the sentence and decide what are the meaningful parts of the sentence and what is the relationship between the words in the sentence. This attention allows you also to train large amounts of data in parallel. Unlike in recurrent neural networks, which were processing data sequentially, attention allows you to look at different parts of the sentence in parallel, which makes these models very trainable on GPUs. And in fact, the encoder and decoder looks like that. So it's not only a single encoder and decoder, but a stack of those. And now you can imagine why do we have these billions of parameters. So this can go deep and very deep. And so far what I've described you, I mentioned text many times, so it works for text. Initially, transformers were used to predict what comes next if you give some certain prompt as a text. If you want to work with the images, so for example, if you want to provide a prompt and we want to generate a new artistic image or photographic image, we need to rely on an extra technology. This additional technology is called diffusion. And in the rest of my talk, I'd like to focus on diffusion, and I'd like to demystify how diffusion works and how you can actually fine-tune diffusion models. What are the typical use cases of image generation? We can recognize basically two main categories. The first one is unconditioned generation. It's basically for unconditioned generation, you train your model to generate specific types of objects, and you don't even need to rely on text prompt for that. So you can, for example, generate human portraits. This is very useful if you want to train discriminative networks to recognize people in the images without using real people. It can be used for synthetic data if you want to populate like a virtual world with 2D or 3D assets. You can use these approaches for that. And it can also be used for super resolution. You can create larger images if you have like some tiny image and you want to make it crisper and nicer. You can also use this technology. And of course, the second category is condition generation. It's the fun one because here you as a creator you can have like actually full control on your outcomes. So you can provide a text prompt, and based on this text prompt, you can generate an image, a photograph, a video, or even a 3D. So it's really exciting to work with this technology. And a little bit of history. Actually, it all comes from the year 2018, when NVIDIA has presented the StyleGAN paper at the CVPR conference. StyleGAN was, it was a GAN-based generative AI architecture which would generate human portraits. And it was kind of groundbreaking because the quality of these portraits was so realistic. And it was really hard to distinguish between a generated portrait and the real photograph. Then it continued with the approach like GAN, which was used for landscapes. And then probably all of you remember how OpenAI have introduced DALL-E a while ago, which felt like almost like magic. And Google has developed a similar approach called Imagine, and somewhat revolutionary in this field was the approach called Stable Diffusion. And I say it was revolutionary because its creators, they actually open sourced the whole architecture, and they've published the weights of the model, which opened the door to the whole community and enabled everyone who wants to work in the field and who want to contribute in the field with the capability of working on it. And the whole field has been developed so rapidly since, and now we are seeing models like Stable Diffusion XL, which provide even more impressive results. And it's not stopping there, so now we also see advancements in 3D generation, in video generation, and it's really exciting. What was my personal motivation to learn how this technology works? I tried this app some time ago where I could upload a bunch of selfies and it would generate artistic portraits of myself. And I really wanted to learn how to do that in order to be able to generate as many portraits as I wish. And these portraits I'm showing you were generated not with the app, but I've generated them on myself by fine-tuning also Stable Diffusion architecture. And I'd like to share with you how to do that. There was another experiment I've done even earlier, and for this I basically trained, fine-tuned a model to transfer style from the Lion King movie. I used to love it when I was a child, and then I wanted to generate pink panthers in the style of Lion King. There was a while back with an older architecture like Stable Diffusion 1.5. And these days, I imagine the quality would be even more impressive. So how does it work? Basically, diffusion is not a model. Diffusion is a pipeline of several components. It's a pipeline of several models. And the main components of the diffusion are actually, well, first of all, clip. It's the transformer part of the architecture. It's the part which allows you to take the control over your generation and to input some text, and based on this text, generate some meaningful result. And the second part is the autoencoder, which allows you to make it more efficient. And the third part is the unit component. So let me go through them one by one. On this image, I'm showing you a typical unit architecture. Those of you who've been in data science for a while, you know that it's a popular architecture which has been used largely for image segmentation. It's still used quite a lot until today, and it's really impressive how it works. So in the input of this model, you usually provide an image and a segmentation mask. And your goal is here to predict the segmentation image on its own. And the way how it learns is basically you have a set of the downscaling components and upscaling components. And on each of these steps, you basically apply some convolutional filters in order to extract the meaningful information. And then you compare your predicted segmentation mask with the segmentation annotation provided by the user. When applied to diffusion, the way it works, we actually we are using this architecture to generate noise. And you may wonder now, we want to generate artistic images. Why are you telling us we need to generate noise? Turns out that if you generate some certain amount of noise and you subtract it from a very noisy image, and then if you do it iteratively for a number of steps, you can arrive at from a very noisy image to something very clean and clear and nicely looking. So to train that, you basically need many images, like millions of images, hundreds of millions of images. And in the input, you provide an image, and you use some sort of a noise scheduler. By doing that, it's kind of a supervised, but it's automated, so you can consider it unsupervised. So you use this noise scheduler to generate the amount of noise. By doing that, you know how much noise you're adding, and you know how the noise is distributed. And then you're trying to predict the noise in the image, and then you subtract it, and then you keep learning by that. When it comes to inference, it's also a little bit different when compared to image segmentation. So here, you start with like a very random noise. And from this very random noise, you iteratively try to predict the amount of noise by using this trained unit, and you subtract it. And you usually do it the number of steps. So typical number of steps is like 50, but there are approaches which allow you to make it shorter, and there are different techniques. So it's really interesting and fascinating how you can get from this very noisy image to something clean and crisp. This works great, but yeah, if you have large images of large resolutions, you can imagine that it will be computationally inefficient, and it will also put a lot of pressure on the memory requirements. So there was a clever idea to optimize this by applying a technique called autoencoder. So basically, autoencoder is an architecture consisting of two networks, encoder and decoder. Encoder takes your original image and it compresses it into the so-called latent space. You can then take your unit and you can train it, and you can make the predictions in the latent space. By doing so, you reduce the number of requirements of compute and memory dramatically. And then once you have done your prediction, you can still upscale your image by using the decoder part of the variational autoencoder. And you can imagine that training this network is kind of straightforward, because what we are getting in the output should ideally be the same what we are entering in the input. Another important, when not the most important component of the text-to-image pipeline is the so-called text encoder and image encoder. The one I'm showing you is called CLIP, but there can be many architectures like this one. CLIP has been introduced by OpenAI and is designed to map the embeddings from the image space to the embeddings in the text space. You can imagine that if we are using different transformers, image transformer and text transformer, we're getting very different embeddings because initially the data is different. So the idea is to make them being used interchangeably, images and text, by mapping the embeddings from one domain to another. And you can do this also, for example, for the sound embeddings. You can map sound embeddings to the text embeddings. And there was also a really nice research by Meta who were able to show that if you train a network which maps the embeddings from text to image and then from sound to image, you actually don't need to train the image to sound mapping because they will be already converging, which is really fascinating. So in this approach, how do you actually bring these embeddings to the same space? First of all, they will be, of course, very different. And then you compare them using cosine similarity. And based on the outcome, you compute the so-called contrastive loss function. If they are very similar, you give it a higher score. And if they're dissimilar, you penalize it by giving a low score. And for this technique, the contrastive loss, you also need some negative examples. And based on that, you basically update the weights of your encoder or decoder, and by doing this, you arrive at the same embedding space. And now, if you are using the text to control your image generation, you can be sure that the generated outcomes will be from the same embedding space. So putting all these things together, how it works. So we have our original image, which has been downscaled into the latent space. We have our generated noise amount from some noise scheduler. And we have the text embedding from the CLIP model, right? Then we have our unit component. It all gets combined together into the so-called cross-attention layer. And we still have the skip connections from the unit, and then we predict noise. And then we run it, like during the inference, we run it iteratively, we reduce the noise from the image, and we arrive at a nicely generated result. It's also possible to do it for image to image. So if you prompt your model not with a random noise, but with some, let's say, prepared sketch, you can further evolve it to nice artistic results. So here, it was my attempt at drawing a Pink Panther. Please don't judge me, I'm not a professional artist. But luckily, I know how generative AI works, and I can make it look nicer. So I've asked the Stable Diffusion model to generate me a Pink Panther based on that, and that's what I got. I was like, well, that looks cool. What if I ask it to generate me a cat? And I got a cat. But then somebody, not very nice, told me, it actually looks like a bear, what you draw. I'm like, okay, and it gave me a bear. But then I was feeling very creative, and I've asked it to generate me a monkey, a cow, and even a pig. So you can imagine I had lots of fun doing this exercise. I also promised you to tell you how to fine-tune these models to generate artistic portraits of yourself. And essentially, what we need here is a Stable Diffusion model as a base model. And there are some certain techniques which allow you to, to fine-tune the model into thinking that, well, some specific objects should look like you. For that, we need our input text. And this OHVX, it's a specific token. We will learn this token to be associated with your specific object, in that case, your portrait. And we'll update our text encoder or diffusion model accordingly. And then we have our training sample. So the next step, what we do, we generate embeddings with the text encoder, including your specific token. We also take our training sample, and we create a very noisy image and a less noisy image. Let's say in our noise scheduler, we stay a step before this noisy image. We then take this very noisy image and text embedding and go through the unit with them. In the unit, we're trying to predict, you remember we're predicting noise? So here we're predicting a noisy image, and we expect this predicted noisy image to be similar to this noisy image of the previous step. We then compare them using cosine similarity. We estimate the loss function, and based on this loss function, we update the weights of our diffusion model. There are also different techniques to do it without updating the weights of the unit model, and the method called textual inversion. In textual inversion, instead of updating the weights of our unit, we do all the same here, but we update the weights of our text encoder, which is another way of doing that. We can also do it in the hybrid fashion, and we can do both. We can update our unit weights, and we can update the weights of our text encoder. There is also another cool technique, which is called adapters. And also, well, very popular adapters are called LoRa adapters. In this scenario, we're doing here all the same, but instead of updating the weights of our unit model, we are including a small piece of matrices, and we update only them. This technique has a very big benefit. If, for example, you know that if you're fine-tuning something, it's in general a good practice to save the checkpoints of your model, right? And checkpoints of this unit model can be big. So usually it's up to several gigabytes of data. And when I was training this, the biggest problem I was experiencing, I was running out of space on my hard drive very quickly. With LoRa adapters, you don't have this problem, because a typical LoRa adapter is just several megabytes, and you can create as many checkpoints as you wish. And the way how LoRa works, it's a very simplified way, but you have your input data, you have your original layers of your unit, and then you basically sandwich these LoRa layers, and you include them, you integrate them in between the original layers of your unit. By that, you are able to enforce a completely new behavior on your pre-trained Stable Diffusion unit part. Another great thing you can do here, you can be very creative. Once you have trained your model, you can rely on text prompts in order to post-process your results. So here, the only difference between these 4 images, I was trying different styles. And if you're working with community models like Stable Diffusion, they incorporate lots of styles. I forgot to mention that the model like OpenAI Clip has been trained on 400 million of pairs of data in the supervised fashion. And the way how it was trained in supervised fashion, because you understand you need the image and the text, they basically crawled these images from the internet, and they took the text description from the HTML meta tags. So by doing that, they were able to have this supervision. And so Stable Diffusion has been trained also on lots of images from also some websites which create some artistic work, meaning that you can also sometimes specify a specific artist and create a piece of art in their style. It's really fun, and you can be really creative here. Another interesting observation I've made running my experiments is that punctuation in your prompts really matters. And by the way, you can have a prompt where you request something, and you can also have a negative prompt in addition, where you want to specify the things you do not want to see in your image, like low quality or like two heads. Sometimes things happen. And it apparently, what I've discovered is that punctuation really matters. Like if you change like the way how you put commas in your prompts, if you put some brackets in your prompts, the results will be dramatically different. Another interesting thing I've discovered is that there is bias in prompts. So in this experiment, I was asking to generate an image, and these are the only differences I had in prompts. So here I've asked to have New York in background, and here I've asked to generate Chinatown in background. You see how it affected the facial features of the portrait. So when I asked for Chinatown, the person in the image looked more Asian. The same happened when I chose specific artists. So when I chose an artist with a European name, it looked more European. When I chose an artist style with an Asian name, the person started looking very Asian. Another great thing with these prompts, you can actually blend them. And you can say, OK, I want this prompt, and you can add some weight to this prompt. So you have the full control on blending this. And then you can kind of create some interpolations and also really interesting results with this technology. There are also other techniques which allow you to do fine-tuning even without, to allow you create your artistic portraits even without fine-tuning. And one such a zero-shot learning technique I found when I was doing my research is called Instant ID. The idea of it is basically very simple, actually, but very nice. So you have a face detection network which detects a face in your image. Then you use another network which has been trained to extract specific embeddings from your face. And then you take these embeddings and you put them as LoRa adapters to the Stable Diffusion model. And by doing that, without any training, you can create artistic portraits of yourself in different styles. I think really very nice idea. Unfortunately, there is a downside that with this approach, you cannot, for example, change facial expressions or head pose. It will be always the same as in your initial photograph. But still very nice. So these are my results, which I achieved on my image with this technique. So you can see that it's quite impressive. And to finish my talk, I'd like to show you the video on what we are working on at NVIDIA. We're developing our own family of models called Edify. Well, one model which already exists is Edify image-to-image. We have trained it in partnership with Getty Images on their dataset. It's commercially safe to use because we make sure that we don't violate any rights on the information with this model. So we don't use any artistic information in this model. And it can be further fine-tuned if you want to add your own artistic style in the model. We are also working on our image-to-video, text-to-video model, and text-to-3 model is also available. We have partnered with Shutterstock to create this text-to-3D. And with these approaches, you can basically generate many different things. So build virtual worlds, build digital twins. The possibilities here are really limitless, and I'm excited to see what comes next.
the future holds. Again, in just a year's time to see that. Unfortunately, we don't have time for questions. However, NVIDIA is going to be downstairs. They have a booth. Ekaterina is going to be down there as well. So please do go downstairs, especially in the networking time. The next panel discussion will be happening in the next few minutes, so feel free to stay if you'd like, or go to the next room.